Assalamu alaikum. I am Mohammad Ikram Hossain. In this video, I am going to show the rectangular waveguide, its properties, its structure, and the derivation of general equation for rectangular waveguide. So, at first, the definition of rectangular waveguide. A rectangular waveguide is a hollow metallic rectangular waveguide is a hollow metallic is a hollow metallic structure with a rectangular cross section that confines and guides electromagnetic waves, typically used in microwave high frequency application to minimize signal loss. So we know any waveguide. Okay, the purpose of waveguide is to guide electromagnetic wave. Okay, so anything that guides electromagnetic wave, it's known as waveguide. And why it is called rectangular waveguide? Because the cross section of it is look like an rectangle. Okay, so it's just like a two parallel plate waveguide. Okay, if we recall parallel plate waveguide, we see this is, if this is one plate, if this is another plate. So maybe if this is the x-axis, in x-axis it was infinitely long. Okay, so but in y-axis we have a finite difference between the plates, that was called d. Okay, so in case of parallel plate waveguide, in x direction it was infinite, but difference in the rectangular waveguide is that both direction x and y, the lengths a and b, both of these are finite. These are not infinite anymore. So our equation calculation becomes a bit um, complex than the parallel plate waveguide. We have to consider everything. In previous case, if it was just like this, if it is in x direction, then the derivation in x direction becomes 0, so it becomes very much easy. But in case of rectangular waveguide, it will be a bit complex. Okay, so here are some properties of rectangular waveguide, that it only supports TE mode and TM mode. It does not support TM mode. Why it does not support TM mode? Because in TM mode, when the wave will enter the rectangular waveguide, it will be just reflecting in both plates, in all of the plates, and it cannot exist in TM mode. It can either exist in TE mode or TM mode. Okay, so in the direction of propagation, at least one of the components, either electric component, magnetic component, will exist. Okay, we cannot actually nullify both the components. And another thing is that rectangular waveguide are actually used in transmission lines or transmission mechanism. We have seen in our lab, in the waveguide lab, the lab 5, that rectangular waveguides were used. So in the next thing, we'll go for the solution of rectangular waveguide. So because before going to the general solution of the rectangular waveguide, we need to remember some of the general solutions for TE wave and TM wave. So for general solution of T wave, if we can remember from Maxwell equations, we have derived this equation for Hx. In case of T wave, actually Ez is 0. Okay, our Ez is 0, and in case of TM wave, our Hz in z direction, our magnetic field becomes 0. So we have derived this equation earlier in our lectures, and these equations will be helpful. This was also helpful in parallel plate waveguide, so we'll be using the same equation in rectangular waveguide. Okay, so if I show now, and there is another equation. This comes from the Helmholtz equation. The upper four equation comes from the our Maxwell equations, and the bottom one comes from the Helmholtz equations. We have seen our derivations in our class. So if I go to the next slide, now we'll derive our general equations for rectangular waveguide in TE mode. Okay, we'll see TE mode, and TE mode is a bit complex, and we can easily derive the TE mode after watching this video. Okay, so now this is our equation. Okay, this is our equation for TE mode. The Helmholtz equations uh, actually simplifies to this. So in this equation, in our previous case for parallel waveguide, we actually could make del by del x equals to 0, because in del by del x relation it was infinite, so there was no change, so we could easily make 0. But in our case, as this exists, we cannot easily make this 0. So the solution for this differential equation is this. Okay, they are actually for del by del x square we can find one solution, and for del by del y square we can find another solution, and this exists in multiplication format. But this hz is a normal component. Okay, so to actually fit in the our initial conditions, our conditions, we need the tangential components, because we know, for example, if this is the x plate. Okay, plate no not x plate, the plate in xz plane. Okay, so in this plate, as this is in towards y direction, in this plane, at x equals to at y equals to 0, the tangential components is towards x direction. So these tangential components, all of these tangential components become 0. Okay, similarly for this plate also, this plate is at y equals to b. In this plate also, the tangential components, the ex components, always become 0. In this way, actually, we can get for this one. For this one, the tangential components is ey, and at x equals to 0, this tangential component, as this is a perfect conductor, the metallic plates are perfectly conducted. Here no electric field, tangential component of no, there will be no tangential component of electric field. So at x equals to 0, this will be also 0, and at x equals to x equals to a, it will also be 0. Okay, right. So to actually fit in the equations, we'll be finding from hz, we'll be finding ex and ey. So how these equations are derived? Okay, so we'll be taking help of this equation. Okay, ex is dependent on hz, ey is also dependent on hz. So just simple partial derivation, after doing simple partial derivation, we can actually get these two equation. Okay, so now we'll be fitting the our initial conditions in this equation. Okay, so I have already discussed at x equals to 0, like x equals to 0 means this one, x equals to 0, our tangential components ey becomes 0. So we have write this equation, so this gives our b equals to 0. Okay, b prime equals to 0. Similarly, another equation we can write, actually, this plane, at this plane y equals to 0, at this y equals to 0, our tangential component ex becomes 0. So we have written here. Okay, so this results into d prime equals to 0. So we'll put this b equals to 0, d equals to 0 in our first condition, this one. Okay, so this one becomes 0, this one actually nullifies, and this one also nullify. So we'll just get hz equals to a cos kxx into c prime cos kyy. So we can write this, and to simplify our equation, we can combine a prime and c prime and write this as a. Okay, so now we'll use another to our initial conditions. Okay, so let me just erase these parts. Okay, so our another two initial conditions was like at x equals to a, our tangential component ey will again become 0. Okay, and another initial condition was at y equals to b, our tangential component ex will become 0. So here we have given these initial conditions, okay, these initial conditions. So when sine something becomes 0, we can write kx a equals to n pi m pi. So from there we can write kx equals to m pi by a, where m equals to 0 1 2 3. Similarly we can write ky equals to n pi by b. Okay, so kx and ky is actually the components of our wave propagation vector. Okay, so we will be writing this m pi a and n pi b in our original equation, this one. Okay, so this is our equation, and using our initial equations, these ones, the general equations for transverse electric wave, we'll be finding four equation. For parallel we get actually two equations become zero, because there was del x, del by del x, this was zero, this was zero. But now for rectangular waveguide we will be actually getting all four equations, none of them will become zero. Okay, so these are the four equations that we have derived. Okay, so now if we just see, these derivations are easy, we don't need to worry about them. So now if we just see the modes for transverse electric wave, so in our previous cases we got for parallel waveguide we got only t1 t2 mode 1 mode 2 like this. But now as there are two variables m and, we will be getting modes like t10 t01 t11 t20 t02 in this way. Okay, 1 is m and 0 here, 0 is n. Okay, so if we write the cutoff frequency equation, the cutoff frequency becomes 1 by actually 2 pi root over mu e. This root over mu is actually our wc. Okay, so 1 by 2 pi into m pi by a square into n pi by b square. So if we just get the pi outside, this will be cancelled out. So the final equations that we can use is this one. Okay, so from here if we find the lowest frequency, actually lowest frequency occurs for fc10. Okay, lowest cutoff frequency fc10. So why fc10 is lowest? Because we know a is greater than b. Okay, so uh, if we just put here 10, okay, if we just put here 10, this becomes 1 by 2a root over mu e. But if we give 0a, 1 by 2b root over mu by e. So a is greater than b, obviously 10 fc10 will be less than fc01. So this is the lowest frequency, and there is another name for this mode. This is the dominant mode. Why this is dominant mode? This actually this is the lowest mode in both tm and tm electric modes are both excited. Why? Because this will always exist. In our previous one we have seen that if we move from mode 1 and to mode 2, mode 1 will also exist. Okay, it will then operate in both mode 1 and mode 2. Similarly in this way this t10 will always exist. Okay, we cannot cancel this one. Okay, so here this was all about parallel rectangular waveguide. So here actually we have derived the t wave, t for t mode. We can also do it for our transverse magnetic. For transverse magnetic we'll be starting with this equation. Okay, we'll be starting with this equation for transverse magnetic, and there it becomes a bit easy. Okay, there we can the derivations are much easier than transverse magnetic. So we can actually see our slide for this and do the derivations. So that's all from my side. Thank you.